Higgs boson.
Ooh, exciting.
Yeah, and we're going deep. I mean, everyone's heard that it gives mass.
Right.
But come on, our listeners want more than that.
Absolutely.
So we've got research papers, analyses, the whole shebang, ready to get into it.
I am. The Higgs is kind of like a keystone in the whole standard model of particle physics.
Okay.
And if we can crack it, well, it could blow open our understanding of, everything.
No kidding. Forces, the universe, even maybe what it's all made of.
Exactly.
That's what always gets me, this tiny thing having such huge implications. But okay, back up a sec.
Sure.
People have heard that Higgs boson gives mass bit. But what's that even mean?
Yeah. Not as simple as, handing it out.
Right.
We got to talk about the field.
The Higgs field.
Yeah, that. Imagine it like thick syrup everywhere in space. Particles moving through it, they get resistance.
And mass.
Mass. More resistance, more mass.
Okay, so it's not just the Higgs boson itself, but this whole field deal.
Exactly. And this field has a shape, a potential.
Potential. Like what it could be.
Kinda, yeah. Physicists, they picture it like a Mexican hat shape.
A hat?
Yep, weird, right? But the lowest point of the hat, that's the stable state of the universe, like where it wants to be.
So this hat shape,
Yeah.
it tells us something deep.
Oh, yeah. It means the Higgs field could be in different energy states.
Right.
And we're at a specific one right now.
Meaning
way back when, the universe picked a spot on this hat. And that broke some symmetries.
Symmetries like
Fundamental laws being the same everywhere. Breaking those gave us the particles, the forces, everything.
wow, okay. So more than just mass, huh? The Higgs messed with how forces work, the whole deal.
For sure. And that's why it's so hot right now.
Oh.
Physicists are looking for where the Higgs acts weird, deviates from what we expect.
Like it's got its own rule book?
Kind of. We call them anomalous couplings. Could point to whole new particles, new forces.
Seriously?
Totally. Some theories even say the Higgs messes with dark matter.
Yeah.
That'd be huge.
Huge is right. But how do they even find these weird couplings?
It's tough. But we got clever tools. Look at how often the Higgs decays into specific stuff.
Specific stuff like?
Like 2 photons or 4 leptons. Tiny differences from what's predicted. That's our clue.
So super precise measurements.
You got it. And then the math comes in. Multi-parameter fits, effective field theory.
Oh, here comes the headache.
Nah, it's cool. Basically, we're looking for deviations without needing a whole new theory yet.
Sneaky. But gotta be like finding a tiny diamond in the pile of sand.
More like a specific grain of sand in the Sahara. But if we find it, revolution time.
Now that's what I'm talking about. Hey, I read about this self-coupling thing too. What's that all about?
The Holy Grail. Standard model says the Higgs interacts with itself too.
Whoa, hold up. It's social.
In a way. Measuring that self-interaction that's proof of the theory tells us about the field itself.
Why is it so hard then?
Because it's rare. Need to see 2 Higgs bosons made at the same time? That's tough.
So LHC, right. Big smasher.
That's our best bet. But then, gotta sift through mountains of data, real detective work.
Makes sense. So what's next? Bigger smashers?
Well, the LHC is getting upgrades, more power, more data.
Sweet.
And yeah, further out ideas for future colliders. FCC, that's a big one. Way more energy, way more precise.
It sounds pricey. But okay, enough smashing for now. Let's get theoretical.
Love it.
We did mass, forces. But what about, the whole universe's fate? How's the Higgs tied into that?
Ooh, now we're talking. Remember that Mexican hat shape?
Still picturing it, yeah.
Well, it turns out the universe might not be at the very bottom, more like a little ledge.
Ledge. Oh, not sounding stable.
Meaning, it could be metastable, stable now, but a nudge could change everything.
Okay, what kind of nudge are we talking here?
That's where it gets fudgy. Maybe quantum stuff, maybe fields we don't even know yet.
So a random quantum hiccup, and boom, everything's different.
Basically, imagine a tiny bubble of a new vacuum forming.
And then?
And then it expands at the speed of light, changes everything it touches.
Hold on. Speed of light. No escaping that.
True. But good news is, even if it is metastable, that happening is billions and billions of years away, at least.
Phew, okay. Bunkers on hold. But still, wild to think the vacuum itself could change. What other surprises does the Higgs have up its sleeve, I wonder?
Oh, plenty. We've been talking known particles, but what if the Higgs is playing with stuff we haven't discovered yet?
Hidden particles, beyond the standard model stuff.
You got it. Tons of theories predict new particles, and some say, yep, Higgs could decay into them. Finding that would be revolutionary.
It's like a whole secret particle party that the Higgs is the bouncer to.
Love that. But finding those decays, that's the hard part. Truly a needle in a haystack.
So we're talking looking for weird stuff that doesn't add up with what we know.
Right. Unexpected particles, missing energy, all clues. Takes serious brain power to figure this out.
And those future colliders, will they help?
Oh, absolutely. The more Higgs bosons we can make and study, the better our chances of spotting something truly bizarre.
More data, more Higgs. Bring it on.
Oh, it's coming. But the challenge then becomes, how do we even handle all that data? It's a fire hose.
So it's not just building bigger machines. It's figuring out how to analyze what they tell us.
You got it. Particle physics is getting super interdisciplinary. We need computer scientists, statisticians, even cosmologists to make sense of it all.
Wow, it's all connected. Speaking of connections, you mentioned quantum gravity before. Can you expand on that?
Ah, yes. One of the most fascinating aspects, really. At super high energies, gravity becomes as strong as the other forces. And that's where quantum mechanics gets involved.
And Higgs plays a role in this.
Potentially a big one. Some theories, like string theory and loop quantum gravity, suggest new particles and forces that could interact with the Higgs, giving us clues about how quantum gravity works.
So the Higgs, bridging the very big and the very small.
Exactly. But there's one more connection I'd like to explore, something that might challenge some of our most basic assumptions about mass itself.
Okay, you've definitely got my attention now. Let's hear it. All right, so that cliffhanger, right? Metastable universe because of the Higgs field.
Yeah, a lot to unpack there.
For sure. Can we, break down what a metastable universe even means, practically speaking?
Right. Well, first off, gotta remember, this is all based on what we know now about the Higgs, and that's still changing.
Science, always moving.
Exactly. But if it's metastable, think of it like balancing a rock on a hilltop. Looks stable.
But give it a push.
Exactly. It could tumble down. That's the metastable part.
So what's the push in this case? What could make the universe go topsy-turvy?
Now that's the tricky bit. Some say it's quantum fluctuations, tiny random changes.
Quantum stuff is always weird.
Or maybe it's the Higgs interacting with, well, fields we haven't discovered yet.
Oh, even more stuff to find.
Always. Point is, something could trigger this. Vacuum decay, we call it.
Vacuum decay.
Yeah.
Sounds ominous.
It's like a bubble of true vacuum forming, and it expands fast.
How fast are we talking?
Speed of light fast. Nothing outruns that.
Yikes. So if this bubble pops up, we're toast.
Well, the good news is, even if it is metastable, the time scale for this is immense. Longer than the universe has even existed.
Okay, so no need to panic just yet, but still wild that the vacuum itself could change. It makes you wonder what other tricks the Higgs has, right?
Oh, tons. Remember how we talked about looking for weird Higgs interactions?
With known particles, yeah.
Right, but what if it's interacting with particles we haven't found yet?
Hidden particles. Like beyond the standard model stuff.
Bingo!
Yeah.
Lots of theories predict those, and some say the Higgs could decay into them. Finding that Nobel Prize material right there.
So it's like, we know the Higgs is a VIP at the particle party, but there's a whole secret room we haven't gotten into yet.
Perfect analogy. Problem is, finding those decays is tough. Like finding a specific atom in the ocean.
So what are we looking for? Anything out of the ordinary.
Exactly. Weird particle combos, energy that seems to vanish.
Those are our clues.
Real detective work, huh?
You got it. Take serious creativity, too.
Yeah.
We need those future colliders, for
Yeah.
sure. Right. The more data, the better chance of finding something strange.
Exactly, though then we got to figure out how to deal with all that data. It's a deluge.
So not just bigger machines, but smarter ways to analyze what they tell us.
100%. Particle physics is a team sport now. We need computer science, statistics, even cosmology to make sense of it.
It's amazing how it all links up. Earlier you mentioned quantum gravity. What's the Higgs got to do with that?
That's where it gets really exciting. See, at super high energies, gravity becomes as strong as the other forces.
Okay, so like early universe kind of stuff.
Exactly. And that's where quantum mechanics comes in. We need to understand how gravity behaves at the quantum level.
And the Higgs is the bridge.
It could be. Some theories, like string theory or loop quantum gravity, predict new particles that interact with the Higgs. Finding those could tell us how gravity really works.
So we're not just talking particle physics, we're talking the whole nature of reality here.
That's what I love about it. But there's one more connection I want to touch on. It might actually challenge how we think about mass itself.
Okay, you've definitely got me hooked now. Lay it on me. All right, you were saying something about challenging how we think about mass itself.
Yeah, so we've been saying the Higgs field, it's what gives particles mass, right?
That's the whole deal, isn't it?
Well, it might be more complicated. Some physicists are saying, What if it's not the only source of mass?
Hold on. More than one way to get mass.
Potentially. Especially when you get to really high energies, there might be other things going on.
Okay, like what? Spill the beans.
Well, think about strong interactions. The force that binds quarks together in protons and neutrons.
Yeah, those are strong, all right.
Exactly. So strong that some of the mass of those particles might actually come from the energy of those interactions, not just the Higgs.
So it's not just that the quarks themselves have mass from the Higgs, it's the force holding them together is adding to it too.
That's the idea. It's kind of like, baking a cake. You've got your ingredients, sure.
The quarks.
But then you've got the mixing, the baking that does something too, right? Changes the final product.
I'm with you. So does this mean the Higgs is less important now?
Oh, no, not at all.
Yeah.
It's still crucial, especially for the fundamental particles like electrons.
Okay, good. Don't want to dethrone the Higgs just yet.
It's more like the Higgs is part of a bigger picture. Mass might come from a bunch of things working together.
So the deeper we dig, the more complex it gets. Typical.
Isn't it, though? It's like for every answer we get, there are 10 more questions popping up.
Yeah, it's science for ya. But speaking of questions, we've covered a lot in this deep dive. Metazable universe, hidden particles, even quantum gravity. What are the big ones, the things that'll keep physicists up at night for the next few years?
Well, measuring that Higgs self-coupling, that's huge. Need to nail that down.
I really understand that Mexican hash shape.
Exactly. And then, of course, the search for new particles. Finding anything beyond the standard model, anything interacting with the Higgs in a weird way. That'd be game-changing.
Always looking for those party crashers. And what about quantum gravity? Any chance the Higgs helps us figure that out?
Maybe. The more we learn about the Higgs, the better our chances. Might find hints of new forces, new connections we never even thought of.
It's like the Higgs is more than just a particle. It's like a doorway.
To a whole new understanding of the universe, yeah. The discovery was a huge deal, but it's really just the beginning.
Well, you've given our listeners plenty to ponder, that's for sure. Any last words of wisdom before we sign off?
Just this. Even though we're talking complex stuff, this is all driven by curiosity. We want to know, the Higgs is proof of that human drive to understand the universe. Where do we fit in? What are the rules? It's exciting.
Absolutely. So to everyone listening, keep that curiosity burning. Ask questions, explore. You never know what you might find.
And never underestimate the power of a good deep dive.
Couldn't agree more. Thanks for joining us on this one, and we'll catch you next time for another adventure into the world of science.